Today I will continue this series of talks about small cancellation theory for groups of Burnside type. Okay, let's start with general things. So what's as I said, what is the goal of this of my series of talk is to present first from the one side to present the this general some form of small cancellation theory, and actually I already defined. And the second part is to apply the small cancellation theory to Burnside groups. So I already defined, but okay, let me recall. So this is a Burnside groups. Traditionally, so it's M generated free Burnside groups of exponent n, which is given by M generators and identical relation of this group. So we have this, and we consider the case when n is odd and large enough. So I do not specify what does it mean to be large, but okay, that's I probably have to recall some history. So there are approaches to this group. So there's of course the so-called Burnside problem, which asks when this group is finite and when I think everybody knows here the results. So this the first proof that this group is infinite, can be infinite, was given by in a joint work by Novikov and Adyan. And so there are several approaches, but so there's a question just to ask if this group is finite or infinite. It's one thing, but another thing is to understand this group in some sense. So that to find this to determine its structure, to understand what relations can hold in this group and which relations cannot hold, and so on. So this to understand somehow to understand relations in this group. It's not a problem. And infiniteness is just a special case of understanding this group. So there are several approaches. So let me recall briefly what are known approaches. So the first one was an approach by Novikov and Adyan. No. Actually, so that I have to write the 68 and was improved by Adyan 75, etc. So another approach was by Arshansky. So Michal, have you read this proof?
Yes,
of Novikov Adyan theorem? So okay.
I haven't read the Novikov Adyan.
Yeah, I've read.
You okay? Everybody knows something about it. They're very well.
I've read the brief for Arshansky.
Yeah, I also read the book.
So there's a book by Arshansky, of course.
Yeah.
So that's 80. So this the first proof appeared, I think, 82 and so on. So there's another approach. So it was there was a later improvement by Ivanov for the even case and so on. So that's I put dots here. Now there's another approach which is initiated by Gromov actually, and it was a Gromov, the Zhang I think it's 2008, and it was actually it was completely clear if the proof was complete or not. Actually. So there are some things. Okay, it was improved by Remy Coulomb. What is the year? It's quite, so it's 2014. And okay, there was very recent work by Coulomb where he applies his approach to the even case. So it's improvement of the Gromov-Desant approach. So it's more general thing because it applies not to just to Burnside groups, but it actually starts with any hyperbolic group, non-elementary hyperbolic groups, and produces an infinite quotient of this group of bounded exponent. So this so we have n. For all, okay, we consider just odd case. We have here n greater or equal 665. This is quite bigger, 10 to the 10, and this is so no bound, for the exponent. So it's very big. It's very large. Actually. Well, so what's the but it's more geometric. So let me explain the difference. So the main difference I think here is that this approach uses. Okay, let me say a few words about a general thing. So we always represent this group as a sequence with a sequence of like an intermediate groups with partial. So we have this. So we start with the G naught. I wrote this actually in the previous talk. So we start with a free group of with basis A. So if it's denoted by A, and we have G alpha is quotient of G alpha minus 1 over subset of some set of relators. But in our case, for the Burnside group, we have this group of relations are of course just periodic of this form. So we have alpha is some set of words of the form x to the n, so x runs over some set. Okay, let's call it E alpha. Okay, and so we have we define this set of relations in such a way that G infinity is isomorphic precisely B and N. So if we add so many relations of this form, so to guarantee that all elements to the power N will be, so to guarantee this identity. Okay, and so that's the main thing is how to choose this set. So in this approach, these relators are chosen by depths in this sense. I explained what does it mean. Okay, but actually I will use a similar approach here in what I'm going to talk. This is approached by word length. So what does it mean? So if we have this group, then we define the set of shortest words which have infinite order in this group, and we take we take this set for E alpha. There are several different versions of this. For example, we can choose either one, just precisely one word here. So this is one. This element could contain precisely one relator, or we can choose just all shortest. All rods which are shortest and have infinite order. So but it's almost the same thing. So this is what I mean by word length. Actually, this is a more general thing. So that's, of course, this is the result that every non-elementary hyperbolic group has infinite quotient or bounded exponent. It's not new because, for example, there's a work by I think Kalshansky Ivanov when they prove that this is true for this result holds for every non-elementary hyperbolic group. But it's just they just illustrate. So they try to develop another approach. So it's more geometric. So they construct a sequence of metric spaces. Actually, there are some finitely dimensional cell complexes, matrix action spaces on which the corresponding group X. So that's actually the points that we consider we consider metric which is not related to group, but we consider metric which is defined for this metric, for this action metric space. Action spaces. So we define a special metric in each action space. For each rank, we construct specific action spaces, and the relators. These relators are chosen with respect to the metric of the space. So that's by length with respect to metric. So we don't have a length element, but we have this just what's called. We have this. I don't remember this. So that's how it's called. So we have a space. If we have a space, then we on which a hyperbolic or hyperbolic-like group X, and for every element we have a translation length. So by translation length. Okay. Right. Okay, and actually this is the similar thing. So we have a set of elements of minimal translation lengths, and we choose a set of relators, a set of rods which have minimal possible translation lengths in some interval. It's a similar thing. So what I think actually, so if we try to choose relators by length, by some kind of length, here we have word length. So actually this is like we can consider this is like a special case because we just for action spaces we take actually kilograms, and translation length by word length corresponds to translation lengths of the action of the group on the kilogram. So it's a similar thing, and for this approach, if you use a length, some kind of length that we need n large. So it's from the point of view of the exponent, it's not optimal. And this gives we see that this gives a quite small value of the exponent. For which the approach works, and as already said, so this is what I do for this with this small cancellation theory. I try. This is like a part of a larger project. So I try to not try, but okay. I'm going to give a much lower bound than this, and again, so I use this approach by depth. And in the version of the small cancellation theory which I defined, actually in this version this version works for n started from 2000, and again for odd exponent. For even exponent, it's just that it's completely another story. So I do not I don't touch this. So I consider only odd case. Okay, so this is a general picture. But if you consider this approach by depth, so what we need actually, we need a more thorough okay, more detailed analysis of relations. Of course, the main point to analyze these relations of this group. And actually, all things about this limit group are consequences of the proper statement for this group. For example, a word represents the identity in this group if and only if it represents the identity in some of this group. So this is one thing. So we need more actually technique here. And another thing. Okay, let's look how the approach goes. So for example, at some point we have this group G alpha minus 1. Oh, suppose you have. So suppose we know this group. We proved that it is a kind of small cancellation. All this approach actually used this small cancellation approach. In this case, it was very implicit because that's it. This small cancellation condition was not explicitly formulated. This is like a little bit more explicit in this approach. So if one looks to the proof, then one can extract somehow that this small cancellation condition, which is really used. But this is in this papers, this small cancellation condition was explicitly formulated, and the advantage of this approach that if you want to prove something, then we have to use induction. So we know the previous group, and we approve something about the next group, and so we need some because we need induction. We use inductive hypothesis. In the approach, we just like one inductive hypothesis that the group the action space is hyperbolic with some parameters, and so this is conceptually very simple. But okay, let me say in more detail how the proof goes. So assume we have have small cancellation theory for the previous group, and then what? So we develop this small cancellation theory, and assume we have so assume we have a small cancellation condition. We prove check small cancellation condition for rank alpha for G alpha over the previous. Okay, and then, because we check small cancellation condition, then we develop small cancellation theory for G alpha. And then, so we need to define, so we need to define somehow this set of relators. Define E alpha plus 1, E check, small cancellation condition for the corresponding set of relators for G alpha plus 1. So, and the next step is to, okay, how to go to which step? Okay, so we have this kind of induction theory. And in each step, so we define the next set of relators, check small cancellation condition, develop small cancellation theory, and so on. So we need induction here, and if you approach, if you use this approach, so actually we need more inductive hypothesis. So it's technically usually more complicated, and for example, if you look at the Alshansky's paper, this initial paper has, I think, about 50 or 60 pages, and okay, this what I wrote actually, this small cancellation approach with the proof, it takes about 100, from 90 to 100 pages. So I don't know exactly because there are many pictures inside. Okay. So this is like a general thing, and so I formulated some like consequences of the small cancellation theory. So one was this generalized end property, but there are several more which are essential, and one of the most essential is just an analysis of relations of the form x equals y in G alpha, where x and y are reduced. So like denoted in this way. So I probably will not define today what does it mean to be reduced, but okay, just because actually I've already defined it. So I just recall that this is just a set of we define x to be reduced in rank alpha if it reduced in the previous rank and doesn't contain subwords which are close in the previous rank, in rank alpha minus 1, to a very large part of relator. So it's similar, like it's very similar to the notion of a dead reduced form. So this is okay, and so we have to analyze these relators. And the point is that we actually I will draw pictures in the calligraph. So in the calligraph. So my working space actually is the calligraph of G alpha. Okay, of course we have this natural set of generators that's denoted by gamma alpha. So we have a picture like this. We can draw. We can represent this relation like by two paths in the calligraph. One, so we take any initial vertex and say draw a path, one path which is labeled by x, another path which is labeled by y. So this is okay. Actually, this is a very simple case, but I can represent more complicated relations in the calligraph, and it's in this case it's not like it doesn't it doesn't look like we need this picture in the Kelly graph, but actually we need. And the advantage an advantage of drawing of represented relations in the Kelly graph we see later. At least another advantage is this. So we can draw relations. We can represent relations in the Kelly graph, but we also can embed diagrams in the Kelly graph. So if we have a diagram of a representation of G alpha, I just write in this way, over the group. So of course, if you can consider simply connected, so we can map this diagram in the Kelly graph so that every path, so it's actually in a sense we have a map, like map, how to call it? I call it actually combinatorially continuous map of one skeleton of the diagram to the Kelly graph. So we have this. We have series of Katya rebuts, Katya stuff, and they all she also used this notion of combinatorially continuous map of graphs. Anyway, that's diagrams can be mapped. In this case, I formulated a statement which says that if we have this kind of relation, and we consider the corresponding diagram that it's single layered. So this is an important property, and this is a consequence of small cancellation theory. So this means that every cell of rank alpha has contiguity subdiagrams to each of the sections here. And if you map this to this diagram to the Kelly graph, so we get the picture like this. Let me draw this picture in a little bit different way. So we have so the cells of a diagram correspond to loops in the Kelly graph. So we have loops which I call relator loops. Okay, it's something like this, and we have so this is a picture how in the Kelly graph. So we have relator loops here, and contiguity subdiagrams correspond to the blue one. To paths, which I draw here in blue. So these are like I call them bridges, and actually they are labeled by certain words which I call bridge words. So bridge words. And here we have the bridge words of rank alpha minus 1. So this is a loop. These are loops of relator loops of rank alpha. So we have this bridge words of rank alpha minus 1. And what's this? Another important thing is that these pieces, these segments, are small. So in some sense, which I don't specify, these segments small. But actually, there's some explicit bound on this. So what So this is like the picture of. So this is a picture in gamma alpha. So and if you look at this at these pieces, at this, so this is the subpath of this. So there's a path of labeled say x. There's a path of this is another path labeled say y. And if look at this piece, so it's a subpath of the path. Okay, let me just say x path and y path. So let's look at subpath of x path and subpath of y path. So okay. The point is that all these loops are like correspond to relations of rank alpha minus 1. This means that all these loops can be lifted to the Cayley graph of rank and so on. So this is like alpha minus 1 pieces. Alpha minus 1 loops here. So on. And if you look at this, so this loop consisting of 4 paths corresponds to closeness relation of the previous rank. So we have what we have here. We have a piece of rank alpha. By a piece, I mean any subwortable relator of rank alpha. So we have bridges. And we have a subpath of x which is reduced. Actually, the definition of a reduced path is closed under passing to subwords. So it's reduced. And this thing, it's one of the I think one of the principal things in all the theory. I call this fragment. So a fragment. Let's just say by word. X is a word. Is a fragment of rank alpha if over x if first of all x is reduced in the previous rank. Another thing, x is closed in rank alpha minus 1 to a piece of rank f. So if you look at this thing, actually in every approach we find something similar. So for example, if we just formulate and generalize that property for the small cancellation theory. So it can be formulated as follows. If okay, let me introduce like how we measure fragments to a piece, say P of rank alpha. A piece means that P is a subword of some relator. So we have R is P, I don't know, PQ, where R is a relator of rank alpha. I have two R's. Okay. Let me change the notation because I'm not sure. I will always use different letter. Let me this set just not my script R. Okay. Everywhere. So where? Let me denote some sets of words and some more complicated objects and words by script letters. So we have script here. We have script in here. I'm not sure I will use E, but anyway. Here we have script. But G, okay, G will be group A. Here we have script R. So, and we can measure a fragment, like say mu of x is just the size of p. So we assume that p is somehow associated with x over the size of r, over the size of the whole relator. But actually everywhere I consider my special length, so I take this alpha minus 1. Okay, I already defined it in the previous talk. So what it's is like a special length here. Okay, so this means that so the generalized the property says that every word which is reduced in the previous rank, and which is if this word defines if this word is non-empty and defines the identity in the group G alpha, then it should contain a fragment of rank alpha with mu of x more than 1/2. So this is generalized in property. Okay, and because this and we from this definition we see that we have a set of fragments. So we have a fragments in x, we have a set of fragments in y. Say, I don't know, it will be say fragment f here, f1, because because we have a piece here and we have a closeness like this. So we have a fragment here. Actually, we don't have this. It's not word. It's not a word. It's a path. But let me do not distinguish words and paths. Okay. So if you have a word, then this is the definition of a fragment of a fragment word. But in the same, okay, this. I use the same term for path. So for path which is labeled by path which is labeled by fragment word, I call fragment as well. Just simplicity of language. So we have fragments here, and we have say I don't know, we have G is busy, H here, H1, so we have F2, H2, and so on, F3, H3. So we have like a set of fragments in X and set of fragments in which are Fi, which is a set of fragments in Y, which are Hy, and they correspond. We have like a correspondence with these two set of fragments. I call them active fragments. So FHI, FIHI are called active fragments. Okay, with respect to this, with respect to say this pair XY. Okay. And how they related. So this is a thing which is now which shows an advantage of using the Kelly graph. Now I define a relation. Okay, let me use this large part of the board. This is called concurrency. Actually, the term is taken from Novikov-Fadyan approach. So they have the notion of concurrent occurrences. But in my case, it will be concurrent fragments in the Kelly graph. So what does it mean? So first we start with the Kelly graph. So we have fragments that say F and H, the fragments of rank alpha. But in the previous Kelly graph, in the K alpha minus 1. So we have a picture like this. We have one fragment, say, and we have so fragment means we have a close in rank alpha minus 1 piece of rank alpha. So we have here H. We have piece, say P, and we have this bridges which are drawn in blue. And we have another fragment, say F. We have another piece, say Q, and we have closures here. And what is P? P is a piece, which means that it's a subword of a relator, and we consider a line. So P so we consider an infinite line labeled by R. I don't know R. So P is subword of R1 to the infinity. My picture is not very good. Okay. So it will be like L1 is a R1 to the infinity line, which means that it's labeled by this infinite word, where R1 is some relator of rank alpha. We have another infinite line. Say it will be L2 is a R2 line, R2 infinity line, where R2 is another relator of rank alpha. Because Q is a piece. So by definition, F and H are concurrent if these lines are parallel. If L1, okay, what does it mean? We can define for two infinite lines to be parallel if they stay everywhere at bounded distance, for example. This is one thing, but actually this thing can be simplified. So what is a parallel line? So we have two lines. We have line L1 labeled, say R1 to the infinity, and we have another line R2 to the infinity. So we have somewhere a piece of line labeled by single period here, R1. So somewhere we have a piece of line labeled by R2. And okay, they by definition are parallel if, say, if we join the corresponding endpoints and we have the same, the path which is labeled by the same element Z here. So in other words, that these two, if these two relators are conjugate by the same by some element z. So this is from the picture, because we have a look here. We have relation z minus 1 is R2. So we have this relation, but it's not just conjugate, but this conjugation corresponds to the geometric locations of these two lines. So this is the point here. But okay, this is called parallel. So we define this notion, but actually we can simplify this. We can assume for our set of relations. So we can choose our set of relations in such a way that if R1 and R2 are conjugate, are alpha. So okay, because we have this picture in the graph gamma alpha minus 1, this means that this relation holds in the group G alpha minus 1. So if you consider something, okay, we consider some relators of rank alpha, then we should compare them in rank alpha minus 1. So R, so Z minus 1 R2Z, then actually R1, you see that I put here symmetrized set. R1 is a cyclic shift. Oh, so actually of R2. So what I want to do, if we have in our set of relators, I have two conjugate relators. They're not just in the group G alpha minus 1. Then I just drop one of them. I consider I choose only one representative from the set of conjugate relators. So it doesn't so we can do the same from any set of relators. So we can assume this simple thing. And actually, if you remember, I formulated another property of another condition, which is included in my small cancellation condition. So if the relator is not conjugate to its inverse. Remember this? I call this S3. So and this greatly simplifies all the thing here. And in particular, this implies that actually if two relators. So we have this. If R1 and R2 are equal, and and if they conjugate, then actually they are just Z is a Z is a power of R. Okay, every if we have an element of infinite order, then its normalizer is cyclic. That's it. So this is the important property. Okay, let me for it from S3. From S3. Okay, from small cancellation theory, we get the following thing. It's enough to claim about centralizer. Centralizer of every R is cyclic. Centralizer of R in gamma alpha minus 1 or in G alpha minus 1 side. Actually, centralizer of every element of infinite order. But this can be proved. So so this corresponds to the case when all elementary subgroups are cyclic. So everything is cyclic. We don't have subgroup which is with every subgroup which is every subgroup of G alpha minus 1 which is all virtually cyclic is indeed cyclic. So that's another form of this. But anyway, we have this property, and this is and this what does imply is this actually. If we assume this, then actually implies L1 is equal to L2, because you see, you look at this picture. So from this property, we see that R1 is a cyclic shift of R2. So actually, they are lines with the same period. And if you consider the period, so if you consider the same period here, because we have the centralizer of every relator is cyclic, then actually they should coincide here. So what we get? So we assume this like the simple assumption on the set of relators, and we assume this if you assume this important property, the important condition, which is a part of my small cancellation theory, then actually this I can reformulate concurrency just if you have these lines. Actually, I call them baselines for this fragments. So we have a fragment, and these are called baselines for this baselines for this fragment. Fragments are called concurrent if they have if the baselines just coincide. Okay, so that's another picture, but we can consider fragments not in gamma alpha minus 1, but we can consider concurrency in gamma alpha. So if F and H are fragments in gamma alpha, then so this is you see this is the previous rank calligraph, and this is the same rank calligraph. Then and H are concurrent. So it's another relation. If they have concurrent lifts in gamma alpha minus 1 in the telegraph of the previous rank. So let's see an example. So if you look at the picture here, then what we have here? So we have one fragment F1, another fragment H1. And what we have here, we have actually F1 is concurrent. Well, let me denote it by by equivalence sign. Okay. So, but not to H1, but the inverse to H1, because we have one line. So if you leave the picture to the calligraphs in the previous rank, then instead of this loop, we have a line, infinite line labeled by this relator, and we have a picture like this. It's some part of this line. We have this one, which are close in rank F-1, so I have to have this lift of F1. Say, I don't know, F1 lift tiled, something like this. And we have a lift of H1, but not H1, but H1 to the H1 goes in the reverse direction. And this closeness here. So we have this picture can be lifted to the calligraph of the previous rank, and so we have this relation here. F1 is concurrent with H1 to the minus 1, according to my definition. So maybe we can take a break.
Yes.
This is to because this person which is responsible for the coding asked not to make a pause in the camera. So he will just cut out this piece from, and so I make his life easier. Точно, надо было на русском писать, да, еще. Ну ладно.
Сколько минут это на 10, да?
Давайте на 10 минут мы чай попьем, наверное, да?
Да, нам нужно
Можно еще покрываю некоторые термины по-русски все-таки произносить, чтобы у нас не было путаницы.
А давайте, да, ну вот смотрите, какие...
По-английски можно сказать...
А вообще текст у меня по-английски, там, в любом случае. Это согласованно называется. Вот. И вот эта согласованность, она на самом деле фактически та же самая, что в работе Новикова-Адяна. Вот, только она геометрическая.
Сейчас уже работа Новикова-Адяна все-таки она по-русски написана, а тут...
А то по-английски перевод тоже есть.
Есть, да. И там вот этот термин так.
Да, но на самом деле это я его использую еще в той работе почетным, как 96-го года. Как бы оттуда все идет. Сейчас, ну вот согласованность, да, ну вот как бы я просто для тех, кто знает, что там, ну, кое-что знает о работе Новикова-Адяна, я просто поясняю. Вот. Но для тех, кто не знает, можно это все независимо рассматривать, как бы если ссылаться. Вот.
Ладно, спасибо.
Okay, and another thing, because these pieces, these small segments are really small, then we have the property like this. Okay, let me. So, if we measure these pieces, Fi is for active, for pair, for the corresponding pair of active fragments, I have this mu hi is greater or equal some 1 minus some epsilon, where epsilon some small number. So I do not specify what is the specific value of this epsilon, but I don't want just to formulate a precise statement, but I would like just to represent the idea. So this is so it's and if you probably say no, this Novikov-Adyan, so you listened this Adyan series of lectures or courses on this. So this is if you have occurrence, if we have normalized occurrence, and we have an image in the reversal, then then the sizes, the sum of the sizes is close to like n periods. So, but we do not have periodic relations here. We just have a general form. So I have a measure like this. So it's everything without periodicity. But anyway, we have a similar thing here. Okay. But what happens if but there is an analog of the statement which is very useful in the Novikov-Adyan theory. So suppose we have a reduced words, let x be reduced in say rank alpha, rank k. And suppose we have so we draw x as a path in the calligraph, gamma alpha x. We have a picture in the calligraph, And suppose we have two fragments in X. So F and I don't know, F and H are fragments of rank alpha in X. So it's like a statement. So it's a proposition. Let's formulate it like this. And suppose F is contained in H, and F is sufficiently large. F is, I don't know, mu of F actually is something like 2 lambda. You remember lambda is a parameter of small cancellation parameter plus some epsilon. So let me write epsilon today several times, but every occurrence of the epsilon in the board means a different value, but small one. So some small thing. Then actually F and H are concurrent. So if we have two fragments and F is larger enough and contained in another fragment, then actually they should be concurrent. So this is the same thing as for it's a similar statement in the non-Kafka theory. I don't know. It's okay. In another form actually. So if we have two fragments of rank alpha, and if they have a large overlapping part, then they also should be concurrent. So it's another form of this statement. But okay, but assume now that we have some other fragment which say occurs in X. So let me pick some color. I don't know. Let it be green. Something here. So we have several. Okay, and actually let us. So we have this equality, right? And because X is reduced, XY are reduced. Okay. So because actually because Y is reduced, this Y this should be small. Then mu of every, so HI occurs in Y. Okay, mu of HI have an upper bound. It's less than rho. This is a parameter of reduced work. So by definition. So rho is actually I take for rho this value 1 minus 9 lambda. This is a fixed value, but okay, it's not so important. So the point is that it's between 1/2 and 1. So and this means, but if you take this value 1 minus 9 lambda, then from this equality we conclude that every Fi is greater or equal than 9 lambda minus epsilon. So every Fi is big enough. In particular, if you have any other fragment in X, then either it contains some Fi, and in this case it should be concurrent with Fi, or then otherwise it should be like between some Fi's. So let's, for example, let it sum here. So assume we have a fragment here. Not a fragment. Say, I don't know, Fi. K. Another fragment of rank F. So what happens here? Actually, so there's a statement which says that there's a fragment in Y. There's a fragment in Y which is concurrent with K. Why? Because okay, this if that's how to explain this. So this implies actually if you have big there should be a part of X and Y which are close in rank alpha minus 1. So the point is that we have this, we have the transition property of closeness. So that's proposition. Closeness position. So I formulated in rank alpha, but actually we need to use in rank alpha minus 1 here. So if we have, say, X is close, okay, X, Y, Z are reduced in alpha. But actually I consider them as paths in the Kelly graph. So we have a picture. So we have, say, X here. X is close to Y. X and Y are close in rank alpha. So this means that we have this picture. So here we X, here we Y. And Y, okay, Y is contained in, say, I don't know, Y prime, and Y prime is close, Y prime and Z are close. Then X is close with some subpath of Z with some loss. So we have then say X is equal to, I don't know, Z X prime W, such that X, Y and subpath of Z are close. Okay, so you see that if you have two pairs of closed paths like this, so one path is close to another path, and a larger path is close to another path. Now we have this. So the first path is close to part of the third path, but with some loss. So we have a Z alpha W alpha. Actually, this is some bound. Something like 1.5, something like this. But maybe so it's not precise. The bound is not it's not the same as in the text. But anyway, it's something like this. Maybe 1.3. Okay, so we have this closeness transition, but if you look at this picture, so actually we have this part, this close part here, this closeness in rank alpha minus 1, and we can consider triangle like this. So some part of K can be close to the path which to this pink to this pink segment, but it's not. It cannot be large. It cannot be more than, say, lambda plus something. Here we have also so this, but and so we have this like we apply this closeness transition, but in like in a more complicated in a more complicated picture. But okay, that's how to imagine this. So we do not care about. Assume we have just not just this picture, but assume we have just a usual small cancellation group. So instead of this narrow pieces, we just coincidence. So if you have a small cancellation, then the picture should be like this. Something like this. So all these narrow parts are just trivial, and we have another piece of the relation. So green now. Okay. So this means if we have a piece, the fragment corresponds to a piece. This means that we can draw a relator here. Then we see that some large part of the relator is contained in Y as well. But we can have some loss here, but loss cannot be greater than lambda, because these two loops cannot have a overlap more than lambda's part of each of them. So we have this loop cannot take lambda from this piece, and from the other side we cannot take more than lambda. So this is why this so with this so this okay. Let me formulate another statement. So we have a proposition. So in this picture, if say K is a fragment in X, and K is not concurrent with any of Fi, with any of active fragments, then there exists a fragment L in K, and no, L is for lines. Okay, there is a fragment N in Y, such that L is concurrent with K in this case, and its size is greater or equal than the size of K minus 2 lambda minus another epsilon. So this is the point. So if you have another fragment in X, and it's not concurrent with any of this active fragment Fi, then we have some image of this fragment in Y, but we can have a loss in this size, and this loss is like 2 lambda plus something small. So this is called stability of fragments. And this is an important thing. So if we combine these two statements, this one so we get the following, like a consequence of the whole picture. So assume that X and Y are paths. Okay, that's X and Y form bygone in the telegraph. This is what I call bygone. This is to yes, this is like a loop with which is divided into two parts. Assume that both are reduced. And assume that what is K is a fragment of rank alpha in Y, in X, then there exists a fragment. There is a fragment of rank alpha in Y such that K is concurrent with fragment fragment N of rank alpha in Y such that K is concurrent with either N or N to the minus 1. So I write it in this way. And the size of N is greater or equal than 9 lambda minus epsilon. This is in the case when it's an active fragment, and if it's non-active, it doesn't. If K is concurrent with an active fragment, then for N we take the corresponding HI. If K is not concurrent with any active fragment, then then we use this statement and we see that we have mu of K minus 2 lambda minus epsilon. So this shows actually we have correspondence between fragments of rank alpha which are sufficiently large. K should be of course sufficiently large here, at least more than 2 lambda plus something. So we have a correspondence with fragments in X and Y which are sufficiently large. And we have we have correspondence. It's not precise because we can have a loss here. So some which we have, if we have a fragment which is not very large, then it cannot we do not see an image in Y can disappear.
But there is some sort of bijection of finitely many fragments.
It's not bijection, it's not precise. You see?
But if we map this fragment to the one in the opposite side, then we can, if we have some...
We can extract a set which have a bijection. Of course. But this is an important property. And this is maybe... using this, I'm going to show how to prove, how to consider periodic relations, and how they, how to prove this small cancellation condition using the fact that they are periodic. So actually, I think that it's better maybe to stop for today, and I will continue the next time, and the next time will be the last time. Sorry. Так, есть ли вопросы?
Вопрос, а вот для монстра Тарского это будет подходить?
Да, все подходит, да, все прекрасно. То есть это некоторый универсальный язык. Вот. То есть от этого никуда не денешься, просто можно, конечно, каким-то не очень явным виде это формулировать, но если мы хотим очень, так сказать, глубоко все исследовать соотношения, от этого никуда не денешься. Например, если я, честно говоря, там не читал, признаюсь, я не смотрел работу Иванова на 300 страниц почетным, но я уверен, что там просто такие вещи там явно сформулированы должны быть, потому что от этого никуда не денешься.
Просто вы говорили, где-то происходит упрощение, вот это упрощение, оно...
А прощение у нас связано с тем, что мы как бы избавляемся от того, мы максимально избавляемся от того, что, так сказать, что нам не нужно. Оказывается, что если, например, дело в том, что если мы классифицируем по длине, то на самом деле очень много оказывается не нужно. Там все можно как-то все в терминах длины как-то это все рассуждать. И вот, так сказать, описание структуры, нам никакого структурного описания соотношений нам особо не нужно. Нам достаточно того, так сказать, аналога вот этого свойства d, оно в общем, хватает везде. Вот. А когда мы классифицируем по длине, да, ну то есть это разумная, так сказать, оценка на показатель, но при этом приходится очень много исследовать всего. Ну так как бы. Чем сильнее результат, тем, так сказать, приходится сильнее исследовать.
А у меня такой простой, может быть, вопрос.
Да, конечно.
Для примера, вот R1 из чего состоит? Из каких слов? Первый шаг.
Первый шаг состоит, значит, R1 состоит из всех слов, которые не содержат, скажем, вот я не помню сколько, ну, грубо говоря, там 50 периодов других слов периодически. Вот и все. По глубине. Вот, ну вот я собираюсь объяснить, да, но вот значит, сегодня как раз вот уже понятно, что времени никакого нет, но в следующий раз объясню, как, да, еще постараюсь вот это объяснить. Вот я объясню, как доказывается, ну вот это свойство наложения. Вот, смотрите, значит, вот.
Потому что в работах Ольшанского начинается с того, что мы берем слова длины 1.
Правильно. Классификация по длине. На следующем шаге берем...
Но постепенно все равно подбираются все элементы.
Да, совершенно верно. А вот я на первом шаге беру, значит, те периоды, которые не содержат 50-х степеней других периодов.
Понятно.
Вот. И на самом деле, если мы возьмем просто такое множество соотношений, мы уже получим группу с условием малого сокращения. Довольно понятно.
И уже бесконечно заданно.
Да, уже бесконечно заданно, да.